The short answer to the question which is here is IT is not an energy saver. It's an energy enabler. It is not a greenhouse gases saver. It's a greenhouse gases enabler. And there is no such thing as a climate neutral IT company. That's greenwashing. Okay. Now for the long explanation. In the title, you saw energy. I'm going to begin by a brief, actually a long explanation on what is energy. Energy is what enables you to be in this room instead of being in a field growing potatoes, having the time to go through long studies, hope for some kind of retirement, work only 70 hours a week because you're passionate people, take holidays sometimes, travel all around the world, be warm in the winter, get clothes for nothing, have comfortable seats, etc. What I'm going to explain is that energy is all that, but it's not this way that it is seen today, because if you ask to the people that manage energy in the companies where you work, and you ask them what is energy, the first answer that you are going to get is not, it's what allowed the civilization to be as it is. You're going to get this answer. Energy is a bill. Okay? Energy is something I pay. The less I pay, the better I am. And that's the answer that you will also get from households. Energy is an electricity, a gas bill, sometimes a fuel bill. We do remember that in France right now. That's what the Gilets jaunes first complained about. But whatever bill it is a bill. Well, that's a wrong answer. It's a wrong answer, and actually, if you think as energy, if you think to energy as a bill, you will go into a dead end, which is the following. As energy is something that you pay a couple % of what you earn. I mean, if you're in your companies, energy, the electricity bill is going to be a couple % of the expenses. Even in an industrial company, it's going to be never more than 10 or 20% of the expenses. If you take, for example, the National Railway Company in France, SNCF, which is the first electricity consumer in France, okay? Well, energy altogether, not only electricity, but also diesel fuel oil for trains, is 3% of what they earn. So it's an absolute non-subject. Okay? So when you take energy as a bill, it's a couple % of what you earn, so you're going to devote a couple % of your thinking time to energy, and a small fraction of the people that work in the company are going to be in charge of thinking how we should manage energy, and it's not an issue for the rest of the people working in the company. Okay? I'm absolutely certain that all you guys here, you don't have energy into what you have to do every day. You're paid to do something else than bothering about energy. Most of you, and most of the time. And that answer actually is about as sound as if I said your brain is 2% of your mass, so I just don't care about what you do with your brain. What I risk at most is that you lose 2% of your efficiency. Okay? Well, dealing with energy as a fraction of our expenses leads you to conclusions which are as stupid. Because as I just said previously, actually all the modern world lies on energy, and if you remove energy, you remove all the rest. Just as if I remove your brain, well, you are a little annoyed to work and go to the morning, to your job in the morning. So it's not a bill. Actually, it can be a bill, but it's not a bill. A second answer that you will get very often is energy is something that we should save. So that's a Pavlovian answer. You say energy and savings. Okay. Well, wrong answer again, not because we shouldn't save it now, but because it's precisely because we didn't save energy for the last 2 centuries that you are in this room, that we are 7 billion on Earth, and that we eat plenty of meat during our meals. It's precisely because we never saved energy that we got the industrial civilization and planes that brought you here. Most people don't know, actually, because most people don't know when it comes to sciences. We live in democracies where science is not the main driver of decisions that are taken. So it's not something that people look at before making a decision. So if you don't look at it, most people won't know. And actually, the poet is probably the guy who is the closest to the good answer. Energy is, by definition in physics, what quantifies the change in the surrounding world. Energy, by definition in physics, is what quantifies change. Okay? So take that, that's we should go back to this definition each time we deal with energy. This is something which is very easy to witness in the surrounding world. Energy is involved in any of the changes that I'm going to describe now. If you change the temperature somewhere, you have energy which is involved. If you have a speed, which is changed, if you have a shape, which is changed, if you have a chemical composition, etc., etc., etc. Take whatever change that we get in the physical world, and you have energy which is associated, because energy, again, is what quantifies the change in the physical world. And that gives you a first conclusion, which is the more energy you have, the more you're able to master your environment and to master your destiny, which is the reason why humanity has sought using more and more energy since humanity began to exist. It happens that energy has the very bad idea of being driven not by our desires, but by physical laws, because it's a physical notion. Okay? And there is one law which is very important when you deal with energy, which is a very simple law, by the way, which is the law of conservation. The law of conservation is a very simple law. It says that in a closed system, you're not allowed to be Harry Potter and you cannot create energy. Okay? What you can do, what you have within a closed system is an amount of energy that remains strictly constant over time. In a closed system, you can neither create nor destroy energy. That's forbidden by the first law of thermodynamics, which is also known as the law of conservation. Which means that humanity, as long as it doesn't communicate with the outside world, cannot create energy within itself. So to use energy, all we can do is go and get energy in the outside world where it's already there and put it into a converter, which is something which is going to give us a kind of service. The first converter that we have used in time is ourselves. Our body is an energy converter. We eat food, which is plenty of chemical energy, even when it's junk food. And that food, we turn it into two things, heat and movement. Okay, so we are a converter, heat and movement. When you program an API, all that you do is that you create movement in your brain, then movement in your fingers. If we can, I can chop off your two hands. If you can still communicate with the computer with something else, for example, your eyes, I don't even need the movement of your hands. Okay, so heat and movement. Then we have discovered that we could use other converters than ourselves. First, we had domestic animals. Then we had wood fire. Put into ovens and other things, and stoves. And we have then designed converters, mostly made of metal, that can use other types of energies, mostly fossil fuels, that you cannot use because you cannot drink oil, or I don't advise you to do so, and that can give us more heat and more movement than our own bodies can. Okay? That's why we have used this kind of converters. And actually, using more and more energy doesn't mean that you drink more and more oil. It just means that you use more and more machines. So wherever you see energy consumption, think machine use. Wherever you see energy consumption increase, think fleet of machine increase. That's the way you should think about energy. Okay? Energy just quantifies the number of machines that we use. And that's all. And it happens that these machines are much more efficient than our own bodies. So let's suppose that you get up in the morning to go and hike, and let's suppose that you are going to climb 2,000 meters in the day. Okay? So you climb half of the height that you have between Chamonix and the top of the Mont Blanc, for example. That's 4,000 meters. Or 6 times the Eiffel Tower on your feet, not in the lift. That's also 2,000 meters. And when you do this, so you lift your mass against gravitation, that's what you do, and your legs are going to provide mechanical energy to do so. Well, the amount of energy that you yield in a day doing this is a ridiculous half kilowatt hour. So if you sweat for a full day, actually, if you are in some kind of intensive labor, intensive physical labor with your body, all that you can provide is half a kilowatt hour of mechanical energy in the day. If you do this 1 day out of 2, at the end of the year, a human body is able to provide 100 kilowatt hours of mechanical energy. Just that. If you are Arnold Schwarzenegger and you dig 15 tons of earth with a shovel each day, actually 1 day out of 2 because of the blisters, then at the end of the year, you're 10 times more ridiculous. You will have provided 10 kilowatt hours of mechanical energy. Okay, for those who remember, it's only E equal mgh. Okay, it's just the fact that you lift off a mass against gravitation. Well, it happens that when you burn a single liter of oil, you will get 10 kilowatt hours of heat. So in a single liter of oil, which of course is something that costs a ruinous price, €1, $1, whatever, you will get the same heat content as what you have in a full year in mechanical energy of somebody who is using his arms. Of course, you don't convert one-to-one heat into movement. You have Carnot's law that forbids that. And so what you will get out of a liter of oil is 2 to 4 kilowatt hours of mechanical energy. Still, it remains the equivalent of 10 to 100 days of hard work of a human body. Of course, it's not the same price. If I pay my worker at the minimum wage, the kilowatt hour will cost me several €100 to several €1,000, take dollars, it's the same, when the machine is going to give me the same service for a marginal cost of a fraction of a euro. Your purchasing power is here. Leisure, long holidays, weekends, the fact that you don't work at night, that you can study until you're 25, that you can retire, all is there. All is there. Democracies are there too. You might recall that ancient Athens and ancient Rome were a handful of free citizens sitting on an army of slaves. Our modern slaves are on the right there. I will show them. I will show more. So you divide, when you go from the left to the right, the price of changing anything into the environment, growing a potato, knitting a sweater, whatever, manufacturing a pair of glasses, the price of doing anything from matter to a finished object is going to be divided by a couple hundred to a couple thousand, thanks to energy. That's the real power of energy. It even allowed us to get rid of slavery, because if you take a slave, which is generally something that you are not very fond of, I mean, nobody dreams of being a slave, except a very small fraction of the population. When you take a slave, you have to go and get that person against his or her will. You have to prevent that person from fleeing, from killing you, from escaping, etc. And you have to feed that person and clothe that person also. And it's going to cost you, even that is going to cost you 10 to 100 times what it costs to take a machine. That doesn't revolt, and that works 20 hours a day. So the reason why slavery has disappeared is not because your genetic code is very different from the genetic code of your remote ancestors. It is just because it doesn't make any sense to bother with people that don't want to be slaves, and that cost you 10 to 100 times more than machines that don't complain. So when you understand this, you understand something else. It's that today it is not men that produce, it's machines that produce. We are just there to drive machines, okay? Take, for example, a tractor. A tractor is as powerful as 600 pairs of legs, and the driver of the tractor is not plowing the field himself. He is giving orders to the tractor that is doing so. Take a public works machine. It's not the worker in the public works which is building your house or building the road. It's the machine, and the worker is just here to give orders to the machine. Take a truck. It's the truck which is transporting goods. It's not the driver. And actually, some of you people probably dream of replacing drivers by software. They don't like it, but no matter what. If you take a train, it's as powerful as 100,000 pairs of legs. And again, it's not the people that work in the train that transport you. It's the train. It's a machine. A plane is 10 times more powerful than a train. And if you take a steel mill, like this one, it is as powerful as a sixth of the French population, to which I would give a hammer and ask to hammer all day. Okay? So all the muscular power of the French people regarding their arms represents only 6 steel mills. Only 6 steel mills. Okay? And you have just one person at a given time driving a steel mill. Of course, you have plenty of people around, but just one in the cabin driving the steel mill. So energy is access to machines. How did the consumption of energy per capita, that is the use of machine per capita, actually the bottom line of the use of machine per capita, evolve over time? This graph gives you the energy use per capita on Earth on average for the last century and a half. What you can see is that our remote ancestors at the time here were using only wood, and most of the machines that we used at the time were stoves, were the first forges, the first steel mills, precisely, but they were not as powerful as today, some steam machines, etc. What you can see is that the use of wood per capita decreased, mostly because for heat production, then something else, it was replaced by coal. What you can see is that since the beginning of the use of coal, the coal consumption per capita has never decreased in the world. Some of you people probably come from countries where coal is of common use. It's not the case in France, so French people have a tendency to believe that coal is something of the old past. It's not the case. It's an energy of the present. And the reason why is that 2/3 of the coal that we use on Earth today is used to produce electricity, and that is going to connect directly with the world you live in. What you can see on this graph is that oil never replaced coal. Oil came on top because oil is by essence, no pun intended, the energy of mobility. That is the energy that you use to move around goods or people. You see that gas came on top, then hydroelectricity came on top, nuclear energy came on top, and very recently you have this thing that gets all journalists and therefore all politicians excited, but it is a no game changer for the decades to come. It is a no game changer. I will take the opportunity of this graph to recall that there is absolutely no link between the real importance of things in the world and what you can read in a paper. There is absolutely no link between the two. Okay? What you read in the paper is what interests the journalist and what the journalist believes that his audience is interested in. There is absolutely no connection with what is really important in the world. Okay? If there were a direct connection, there would be no need for PR officers. Okay? Journalists would guess by themselves what is important, and they would report on what is important. The fact that you have communications officers everywhere is precisely to influence journalists to say, this is important, what happens in my company is important, and actually, it's not the case necessarily, it's what happens in your company. It's not necessarily more important than the rest, but it's what you want the paper to write about. What fuels the world today is fossil fuels, that is, molecules that are mostly composed of carbon and hydrogen. What you can see on this graph is that at the present time, the energy used per capita is a little bit more over 20,000 kilowatt hours per year, which means that the fleet of machines used per capita on average in the world represents a multiplication by 200 of your own muscular power. In other words, if energy was not there, the production in the world today would be divided by 200. It's another way to put it. I put it another way again. Our standard of living right now in the world is equivalent to the production capacity of 1.4 trillion people. It's another way to put it. Okay? Not the productive capacity of 7 billion people, but 1.4 trillion people. At any time, another way to put it, the power of the fleet of machines in the world is 200 times the muscular power of humanity. And actually, it's 400 times the muscular power of the fraction of humanity which is awake, because half of the humanity is sleeping at the present time. Machines don't have to sleep. What you can notice also on this graph, I won't elaborate much on this today, but it's something to keep in mind, is that you can see that the time at which the energy intake or the energy used per capita came to a sudden halt is the first oil shocks. So the first oil shocks don't correspond to a time or to a special event when oil prices skyrocketed, then they decreased, and the world resumed its evolution. It corresponds to something very special. The energy use, the energy consumption per capita was rising fast, and it came to a halt, very suddenly. And it's from that time that appeared the national debt of most states. Before 1974, there was no external debt for most OECD countries. Okay? It appeared then. Unemployment appeared then. So something very special on the physical flows happened when the oil shocks happened, and actually a normal situation never resumed from that time. But still, we have a standard of living, again, which is absolutely extraordinary compared to what the standard of living of humanity has been for the 20,000 years that preceded. Okay? And it's something which is not going to last for very long. That's the good news of the afternoon. So our modern slaves, here they are, or actually here is a very small subset of our modern slaves, and actually just putting on a dress this morning or a shirt this morning called on thousands of machines that have been working for you. From the oil platform or the cotton field to what you took from your drawer or from your chair this morning, and it took exactly 3 seconds to put on a cloth, again, that called on thousands of machines to be manufactured from primary resources to your house or your home. So this fleet of machines, as I said, that eat a particular food, which is energy, is the equivalent in terms of power to several hundred slaves per capita. So we are all slave masters, all of us. And in the Western world, the level of slave, mastery, is about 1,000 to 2,000 slave equivalent per capita. So most of you that come from Western countries, France, Europe, the US, Australia, Japan, etc., even the eastern part of China is like a Western country, you are a slave master of 1,000 to 2,000 slaves that are machines that work for you. The Industrial Revolution that began 1.5 centuries ago is something which is actually the rise of fossil fuels, as you can see on this graph. Here you have the fraction of fossil fuels in the energy supply of humanity, and what you can see is that it corresponds, you have a strong increase of that fraction between the beginning and the end, well, not the end, and the first oil shocks. And what you can see on this graph is that since the first oil shock, it remained about constant. And what you can see also is that the renewable boom that the papers are boasting about all the time has changed nothing, absolutely nothing, on the fraction of fossil fuels in the energy supply in the world. Because actually the papers tell you that there are plenty of windmills everywhere. They forget to tell you that at the same time, we are still building plenty of coal power plants everywhere. It's a non-renewable computer. Bad slave, yes. Going to be finished tonight. Yeah. I'm going to try another one.
So we need better hardware APIs, right? Connectors, right?
No, it's... I need to probably to get this fixed.
Fixing bugs in production, right?
No, fixing bugs in hardware. You see?
Awesome.
There we are. So, as I said, there is nothing such as a renewable boom when you look at the fraction of fossil fuels into the world energy supply. It's something that exists in the paper. It doesn't exist in the real world. When you look at the real world, here is the global evolution of the energy use. And actually, when I say energy use, again, think of food for machines. That's what it is, really. Okay? And what you can see is that the renewable part here, or the new renewable part here, is something which is coming on top of the rest, which is still growing. And actually, for the problems that I'm going to mention in the near future, what we're interested in is not the fraction of renewable energy, it is the amount in absolute figures of fossil fuels. Because it's the amount of absolute figures in fossil fuels that gives the CO2 emissions, and it's the amount of fossil fuels in absolute figures that you confront to the ultimate reserves. So the fraction of renewable into the energy supply is not the point. I don't care about that. I just care about the amount in absolute figures of fossil fuels that we use. That's the point. Okay? And what fuels the world today, again, is carbon. If you look at electricity production, it remains true. What you see here is that electricity in the world is first produced from coal. And when you produce electricity from coal, you get roughly 1 kilogram of CO2 per kilowatt hour, per electric kilowatt hour that you produce. The second term here is gas, and gas might be natural, but still, it's a fossil fuel. I mean, we say natural because in ancient times, gas that you had in cities was produced from coal and water vapor. Okay? We heated together, we used to heat together coal and water vapor, and that produced a gas which was a combination of hydrogen and carbon monoxide, which is the reason why you could commit suicide with this gas. Now it has been replaced by methane, with which you can't commit suicide, except if you blow up your building. And even that, the result is not guaranteed. But I would say it's called now natural gas because in ancient times, it was not gas coming from fields. It was manufactured and produced in special factories. Then we have oil. We still have oil, about 5% of the electric generation in the world. Then we have the first low-carbon electricity, which is hydroelectricity, and it is by and large the first term in renewable energy, electricity. Then we have nuclear, which is the second low-carbon electricity production in the world, and then we have the rest. And actually the rest is not so low-carbon when you look at it, because solar panels are today mostly manufactured in countries where the carbon content of electricity is very high, namely China. And if you get a kilowatt hour from a solar panel, it will be, because of manufacturing the solar panel, it will correspond to 50 to 80 grams of CO2 per kilowatt hour. Okay? So it's lower than gas and coal, but it's not zero. And if you store that kilowatt hour on a battery that you have to manufacture, and manufacturing batteries is basically metallurgy and chemistry. So it's using plenty of energy. If you store a kilowatt hour on a battery, the fact that you store and unstore the electricity is because of the manufacturing of the battery, is going to correspond to anything in the range of 50 to 200 grams of CO2 per kilowatt hour. So if you add producing the kilowatt hour from a so-called zero carbon electricity, a solar panel, store it into a battery and restitute it afterwards, you're anywhere in the range of 100 to 250 grams of CO2 per kilowatt hour. If you take it from a windmill, it's only 50 or 60. Okay? But it is not zero CO2. It is not zero CO2. Still, it is something. Still, you have to manufacture metals, and you have to have basic chemistry. When you look at the change in the electricity production in the world over the last 7 years, what you can see here you have the increase of each type of energy that we use to produce electricity. And what you can see is that the production that most increased over the last 7 years, is not any type of renewable production, it is coal. Okay, it is coal, and then comes gas. So, if I summarize what I've just been saying, energy is mechanical slaves. Those mechanical slaves mostly eat oil, gas, and coal, and not renewables energies or whatever else. But we think of energy as a bill. Actually, economists also think of energy as a bill and only as a bill. In the economic world, which is the world you are living in, because you might be paid by someone, that's part of the economic world. You might spend money on buying things, that's part of the economic world. So wherever you have a price, you're in the economic world. Well, when we designed a productive economic system, about 2 centuries ago, the economists at the time said, okay, we have 2 productive factors. We have people work, we have human capital, and once we have people and human capital, we get the production. That's the economy that you learned at school, right? Is there anyone in the room that learned something which is different in school? No one, okay. Well, this is true and false. When the economic system was designed, or when the economic thinking, sorry, was designed 2 centuries ago, we were 500 million people on Earth, mostly peasants, with a productivity per capita that was very low because we had the help of very few machines. And so, indeed, the limiting factors at the time for the human production was the number of people able to work and the amount of human capital that we had already accumulated, no matter whether it was owned by the state or by individuals, okay? Human capital as an accumulation. But today, this first order approximation, that is that the 2 limiting factors are only people at work and human capital, have become false. We have an excess of capital. There is plenty of money everywhere that we don't know where to invest, which is why the unicorns get valuated at absurd prices. And we have too many work because there is unemployment everywhere. So actually, the 2 factors that we thought were the limiting factors of economy today are the 2 factors that are in excess. Because the economy needs something else for production to exist. All the atoms that you have in the products on the right, you have to get them somewhere in order to produce these objects. So we need natural resources to make the objects and to make the services that we produce at the end of the economy, as an output of the economic system. Okay? There is no way you can manufacture the chairs on which you are sitting without atoms. You just cannot do that. You cannot sit on a concept of chair. Okay? You need to sit on a chair. Well, these chairs are composed of a subset of the 92 elements that you have in the table of Mendeleev, and these elements in the natural world, those are natural resources. They are not arranged the same way, these atoms, so you have to change the arrangement, that's chemistry. You have to change the shape, you have to transport it, so you have to transform in a way or in another. And when I said transform, that means you have to use energy. And the energy that you use to transform all that is called work. And in physics, actually, work is a particular form of transformation. And that work today is provided for 1 by our own bodies, and for 200 by the fleet of machines that we have in the world. And now you understand, and the capital, sorry, is an internal loop. For example, the computers that you have in your companies, which is in the capital column, they have been produced just as your shoes. Take natural resources and transform them with our work a little and machines a lot, because you are not able to melt silicium with your hands. Because, again, you are not Harry Potter. Now, if I lack energy, I will lack the ability to operate part of the fleet of machines, and at the end, I will lack production. So there is something else that we should look at when we want to forecast the volume that we produce. It's the amount of energy that we can put into our machines. It happens that we don't look at this volume, we look at the price of energy, but we don't look at the volume, and there is no such thing as a long-term elasticity between prices and volumes for energy in the world. So that's also something that you learned in school. When there is less of something, the price increases. Well, if I showed you, I'm not going to do this today because I don't have enough time, but long series for energy, it's absolutely false. There is absolutely nothing that resembles an elasticity in the long run. And it's true actually for any commodity. Cereals, iron ore, gold, whatever, there is absolutely nothing that resembles an elasticity in the long run. Not for a single commodity, okay? Somebody in the room thinks the opposite. I take the bets at the exit when we leave. You also need natural resources. And if you lack natural resources, same thing, you will lack production. So for example, if you lack indium, then you don't manufacture computer screens anymore. Even if you have plenty of skilled workers, even if you have plenty of investors into Palo Alto, and even if you have plenty of energy. Okay? No indium, no computer screens. In the ancient times, it was indeed not a limiting factor, natural resources and energy. And that's the reason why, for ancient times, the economic theory works very well. At that time, you had no population growth, or very little population growth, no machines, so basically you had no GDP growth, which was very convenient for elections. No need to promise growth, but actually you had no elections at the time. And it's a good question for me to know whether our democracies will remain stable in a world with no growth. My bet is that the answer is no. So it might turn out that in 20 years from now, either you will work for dictators or you will be out of work. I'm very serious. I'm very serious. And we have put all the big brother we need in place for the future dictators to come. They will say thank you. Until the beginning of the Industrial Revolution, there was already the help of machines. Actually, it began at the end of the Middle Ages. Machines, more and more. So we had a little growth. And actually, the democratic system appeared in UK, which was the first Western country to experiment a growth over what existed in the other countries. And then, that's the beginning of relatively, we have fossil fuels fueling plenty of machines, and then, there we go. And we have economists that say that we are going to get long-term structural growth. That's a big fat joke. Okay. It's Boulder that said, I think, if you meet someone who says that perpetual growth is possible, it's either a mad or an economist. And you can merge the two. Actually, sometimes it's an obligation. This is the best macroeconomic model I know. The best macroeconomic model I know is a straight line. Tell me how much energy you put into the fleet of machines. I'm going to tell you how many machines work, so I'm going to tell you what is the value of the output of the machines, that is the GDP. It is very simple. What you can see is that there is no such thing here as a long-term gain of efficiency. Okay? If there is one, actually there is one, microscopic. And because most energy is fossil, this is the COP predicament. You just cannot escape fossil fuels if you want growth. So as long as we say in the United Nations Sustainable Goals, we want both economic growth and a stop to climate change, you're doomed. You just won't get a stop to climate change. You will get a stop to CO2 growth, though, because you will get a stop to CO2, to a fossil fuel consumption increase. That's because of mass. I'm going to tell you in a couple of seconds. But decoupling for real is something that we just cannot achieve because the fleet of machines that we use around just cannot be converted to renewable energy very fast, and actually not in the volume that we use today. Because I recall that a renewable world is the world that we are coming from. 2 centuries ago, the world was fully renewable. We had renewable wind to power our boats, and we thought that it was preferable to put diesel into the boats because it was more efficient. We had renewable grass to put into the oxes for the plows. That was perfectly renewable, and we thought that it was much better to put non-renewable petrol into non-renewable oil into tractors. We had renewable clothes, mostly wool, and that was about it. Cotton was not accessible much in Europe before we had trade. Now we have non-renewable synthetic fibers, and we think that it's much better, etc., etc. So we come from a renewable world. And I can tell you that there is at least one renewable experiment that works for real. It's the world 2 centuries ago. That works for real, I'm sure. A high-tech society of 7 billion people running fully on renewable. I also take all the bets at the exit gate, and I transmit it to my kids against anybody who wants. That at the present level of GDP, it's absolutely impossible. It is absolutely impossible. So addressing climate change for real means that we trigger a recession. Now, the good news is that it will come anyway, That's the good news. But because of the limitation on fossil fuels and the limitation on natural resources, we cannot transform more and more resources forever on a finite planet. Okay? But we have to understand that it is not possible to have both division by 3 to 4 of the CO2 emissions in the world and a GDP that remains at the present level. That won't happen. That will never happen. This is something that also explains the importance of energy. Here you have a graph on which the green curve gives you the year-on-year change on the energy supply in the world. So that is the fleet of machines that work in the world. And the blue line is the year-on-year change on the GDP in the world. And you see they are very finely adjusted. You have no such adjustment if you take the population year-on-year change, or even the population at work, year-on-year change, or if you take the year-on-year change of the capital that is available. Okay, either one or the other is not fitted to the year-on-year change of the GDP as energy, that is the fleet of machines is. I'll put it another way. The last 2 centuries have been this story, in short. We have fossil fuels under the ground, and they are free. Oil is as free as air. Air is free. Okay? Nowhere in the economic equations you have the fact that we have air, which is why a number of people say as air is free, wind is free, so we should use wind because it is free. But I've got good news for you. Oil is free. Nobody in this room paid a single cent for oil to exist. I mean to exist, to be formed. So the formation of wind is free and the formation of oil was free. All it takes in both cases is to pay the guy that has the good idea to sit on it, so either on the oil or in the field where you are going to erect the windmill. In both cases, you pay someone, or you just run him over with tanks and planes. We have done both. And the second thing that you have to pay for is the workers that are going to go and get the energy. So in the first place, people that manufacture and erect the windmill, and in the second case, people that manufacture and erect the drilling machines and all that you use to extract the oil. But in both cases, the energy itself is free. So oil is a fuel, it burns. It means in chemical terms that you can oxidize it, and get energy from that reaction. And the energy you get is going to allow the transformation of all the rest, and is going to allow the increase in the productivity of work that has allowed to put all people in cities. So cities is a result of abundant energy. When you plot in the world the fraction of people living in cities against the energy consumption, you get a straight line also. So the idea that in a world which is running short of energy, we will all live in cities playing video games all day is a hoax. We will go back in the fields and grow potatoes. We will go back in the fields and grow potatoes. And when you look at some places in the world where you have the energy availability, which is already decreasing, what you see is not at all people going to the office and playing video games. It's not exactly what you see. Okay? And the way we count all this is through an annual flux, because I recall that the GDP is a flow. It's not a stock. Okay? It's the monetary value. It's the price of all that we have produced in the year. So you don't get richer because the GDP increases. It just means that you have transformed more. If you get richer, it means that the value of your assets is growing faster than the value of your debt. But here, we have no debt. We have built a system with no debt. There is no amortization of the natural resources when we transform them. Okay? We should amortize the remaining oil, for example. There is less. We take something into account in our balance sheet to account for the fact that we have less oil remaining at the end of the year. We don't do that. So actually, it's something that cannot grow forever, because we forgot. Actually, we have no accounting which is the equivalent of a net result. We only have an accounting which is the equivalent of a gross turnover. Okay? But you can increase your gross turnover and go bankrupt. Absolutely no problem with that. Two limits to this. The first limit is that burning fossil fuels puts CO2 into the air, and that is triggering climate change. I'm going to say a couple words on it. And the second limit that we have is that fossil fuels take 50 to 300 million years to be formed, which is to say that they are not renewable in the course of historical times. And so the more we use, the less remain. Okay? The less remain. Regarding the bottom issue, the upstream bottleneck, there is, again, something that we should keep in mind, a very simple math theorem that says the following. When you have an initial stock, which is given once and for all, something that you cannot do is draw from the stock and get each year a production that increases forever. Because if you do this, if you could do this, the stock would be infinite, which is not the case. You cannot even get from your stock each year a quantity which is constant forever. Because if you do this, again, it assumes that your stock is infinite. Actually, maths allow to demonstrate that the only thing that you can get in such a case is an extraction that will start at zero, which is true for any ore or for oil. If you go far enough in the past, you will see that it is zero. Sometime in the future, near or remote, it will be zero again, and in between, you will go through an absolute maximum. And that's not true only for oil. It's true for copper ore, for nickel, for vanadium, for chrome, for molybdenum, for, well, just name it. You will have silver, for gold, you will have a maximum. That maximum is sometimes called the peak. So the peak is not something which is an illusion. It's a math theorem. It is just a math theorem. Okay? And for whatever resource that we get from the Earth crust, and which is not renewable, there will be a peak to the annual extraction. The only question is when, or the only questions, to be more precise, are when, at what level, and whether it's annoying or not, because we can easily substitute by something else for which the peak is much more further in time. But those are the questions, okay? The good news are, for oil, the peak is now, roughly. You have here a projection that was made by oil geologists. It's been made 10 years ago, so they were a little pessimistic, as always. They said that the peak should be today. My belief is that it's a matter of years. Okay? The energy minister in Russia just said that Russia was about to peak in the coming years. Africa peaked in 2009. Europe peaked in 2000. Conventional oil in the US peaked in the 70s. China peaked in 2011. Indonesia peaked in the 70s. I mean, so plenty of countries peaked already. And when you look at the overall oil production in the world, conventional oil, that is all that is not tar sands in Canada, and shale oil in the US, peaked in 2008. And that's now in the International Energy Agency reports. Took a long time to get there. And there you have a remainder from shale oil and tar sands, but it won't replace the decline of conventional oil for very long. So when oil peaks, that is going to trigger a world recession. When conventional oil stopped to increase in 2006, then peaked in 2008, it triggered the Lehman Brothers crisis and what we have called the subprime crisis, which is actually the conjunction of a debt that rose since the first oil shocks and an energy supply that began to decrease in the OECD zone. But when the oil supply in the world decreases in the coming years, we will have a new financial crisis. I don't know where it will start, what will be the magnitude, probably higher than the last one, but we will have one in the coming years. Okay? And bits and pieces are beginning to happen here and there. The maximum of the energy supply in Italy was 2006. The GDP has decreased sharply since then, and they got what you know, that is a political turmoil. Same thing in UK, same thing now in France. I mean, it's the same and same thing in the US with the Trump election. So all these are same consequences, or it's a single type of consequence of an energy supply in Western countries which is beginning to decrease. And the growth that you experience in your sector is now done at the expense of things that cannot grow anymore and decrease even faster in other sectors. Okay, it's just an arbitrage. This use of fossil fuels have triggered rising CO2 emissions and other greenhouse gases. climate change is a very long-term issue because of one physical, or rather chemical property of the CO2, which is that the CO2 is an oxide, dioxide, to be more precise, and oxides are very stable molecules in the world. So once you put CO2 into the air, the surplus that you create is something which is going to remain for huge amounts of time. Actually, the CO2 surplus that we have already created, should we stop to emit tomorrow morning, 1 century after we stop the emissions, 40% of the surplus is still there. Even my computer knows this by heart, shouldn't be afraid. 1,000 years, it's okay. 1,000 years after we have stopped the emissions, we have 20% of the surplus which is still there. And 10,000 years after we have stopped the emission, we have still 10% of the surplus which is still there. So what you have to keep in mind for climate change is that there is no such thing as a reset button. The day we witness something which is unbearable, the only certainty then is that it will get worse later on. Okay? There is no reset button. It is not a video game. Okay? The day we know, the day we witness it is unbearable, because of that time constant, the only certainty that we know is that it's going to be worse later on. So it's a one-time experiment. Okay? We won't redo it a second time. To understand the magnitude of the change, here is a map representing Europe today. Actually, it represents the ecosystems that we have in Europe today. What you can see is that in Europe today, if we don't remove the ecosystems to have fields and other things, such as Google data centers, what we have in Europe is mostly forests. Means that the climate is mild and it's wet. This is Europe 20,000 years ago. 20,000 years ago, the planet is in the middle of an ice age, meaning that it's much colder than today. And Europe doesn't look, obviously, doesn't resemble what it is today. The first thing is that if there are Finnish or Swedish or Danish people in the room, at that time you're buried under ice. And if there are Canadian people in the room, at that time you're buried under ice. There is an ice cap which is 3 kilometers thick, which is posed on Canada and another one on Scandinavia. To form all that ice, water has been removed from the ocean, and the level of the ocean is 120 meters lower. The ecosystems that we have in Europe at the time resemble what we have today in the northern part of Siberia. And in France, we have a small fraction of Paris that represents the global population able to eat berries and run after mammoths. Well, when the Earth warmed, because it warmed obviously, to go from the state on the left to the state on the right, it corresponds to only 5 degrees in a couple million years. It is only 5 degrees in a couple million years. So when you look at the magnitude of the change triggered by a couple degrees, what I can tell you is that a climate change of the magnitude of a couple degrees in a century means war everywhere. I'm serious about it. The competition for remaining resources on an Earth populated by 7 billion people will be so harsh that it's going to trigger war everywhere. So it's not a nice to have addressing climate change. It's just as essential as, it's preserving our space shuttle, basically. If we don't mind about climate change, it's about as if the space shuttle was on collision course with Earth and we were still bothering about gender equality and wages into the shuttle. We can, if we want. It's not going to change the outcome. Climate change is not only a change in temperature, it's only a change in precipitations. What you have here is the expected change in precipitation in the world, and what you can see is that in France and all around the Mediterranean basin, what is expected is a severe increase in drought, that is a severe decrease in the agricultural yield, so a severe decrease in food. So prepare for food riots. Everywhere you have the yellow and red spots on this map. Plenty of other things. The day we go over the 2-degree threshold, we are almost sure to trigger the dismantling of the West Antarctic ice sheet, plus 6 meters in the ocean, and the melting of Greenland has already begun, plus 3 to 6 meters in the ocean. It's going to take a couple of centuries, but the day we know that we're over 2 degrees temperature increase, if there are Dutch people in the room, your remote descendants will be flooded. You're sure of that, the day we go over the 2 degrees threshold. It's just a matter of time. A couple centuries, again, not tomorrow, but still. And it's not reversible. And you have plenty of other consequences. Hurricanes will increase in intensity, etc., etc. If we don't want to play that game, where is the limit? Well, as I said, CO2 being an oxide, it's very stable in the air. And so what counts regarding the temperature increase is not the annual emissions, it's the cumulated emissions, because you cannot remove the cumulated emissions fast. Here you have a graph that plots the world emissions cumulated from pre-industrial times, that is 1850 to be in short, to 2100. So it's how much we will emit in CO2, in billion tons CO2 between 1850 and 200. And here it's the temperature increase that we will get between 1850 and 2100. At the end of 2017, we had already emitted in the world 2,200 gigatons of CO2. So we have already signed for 1.5 degree. So when you see in the paper that people gather at the COP to say that we are going to do our best efforts to achieve 1.5, it's as sound as if I said, when I am 25, I'm going to begin this. I can repeat? No, okay. It will never happen. That's done. Finished. 1.5 is behind us. We will get it anyway. The only question is when. So any time between now and 2100, depending on the remaining emissions, we will get 1.5. That is certain. We're committed to that. If we want only 2 degrees, I can do the reverse. We must limit ourselves to something in the range of 3,000 gigatons of CO2, of which, of course, 2,200 have already been emitted. So it means that your generation, mine, for what I still have to live, and your kids' generation, if you have some, should emit only 1/3 of what my parents and my grandparents emitted in the world, and myself before, when humanity was roughly 3 times less numerous on average. That's what it means, 2 degrees. I can tell you that it's not a little greenwashing from some IT companies which is going to do the job. Not really. Actually, if we want 2 degrees, we should divide the world emission by 3 by the time my kids are my age. So future generations are in this room. I am future generations. Good news for me, I'm young again. There is nothing such as future generations. Doesn't exist. It's present generations. Future generations is a hoax, fake news. Where do the emissions come? Well, 20% of the world emissions come from coal power plants again. 2,200 gigawatts of installed coal power plants in the world. We should get rid of all of them in the 30 years to come. I can tell you one thing that some of you don't want to understand maybe. If we don't massively call on nuclear, you can forget it. Not a single second we will achieve that objective with only windmills and solar panels in 30 years. Not a single second. Okay. 7% is coming from oil and gas, mostly gas power plants. 6% is coming from cement plants alone. 12% is coming from blast furnace for 4%. The rest of the industry for 8%. And in the rest, you have chemical industries which emit a lot. And that doesn't take into account the electricity consumption of industries, of course, which is accounted for in this part and this part of the pie chart. Boilers in buildings, which are mostly present in mid-latitudes. Of course, you don't heat buildings in Singapore, represent 6%. Transportation represents 15% of greenhouse gases emissions. It's not only CO2, also methane, nitrous, product side, etc., of which cars represent 6%, trucks represent 4% in the world, and ships and planes 2% each. Agriculture represents deforestation, which is an upstream process of agriculture, it's because we are more and more numerous and eat more and more meat. Those are the two basic drivers of deforestation, 10%. And then waste management, cooling machines, etc., and other things, 7%. So just name it. Where do we start? We should divide this by 3. Do we take each part of the pie chart and divide it by 3? Do we take some parts of the pie chart and remove it completely while leaving some? Just name it. Okay? So that's the challenge, 2%. 2 degrees. Now comes IT. IT is green, as you probably know. It is very green. Actually, it is extremely green, IT. It's extremely green because it's extremely smart, and if you are extremely smart, you cannot be brown, otherwise you would be dumb. So as there is no such thing as dumb IT, green IT is natural because IT is smart. It is just the same psychological process of saying natural gas. If it's natural, it cannot harm you. Don't laugh. Don't laugh. This is a true process among politicians and among electors. So if it is smart, it is green, okay? Actually, it's debatable. This is the beginning of an IT system. You see, an IT system is packed up with derivatives of oil. You have organic chemistry, which is providing plenty of components or things that are necessary in the manufacturing process of a computer that require oil products. So this is the beginning of a computer. Now you have also this as the beginning of a computer. This is for the glass. This is for building factories. This for transporting elements. This because you have mining industries. This because you need purified water. This because you need to melt steel to manufacture antennas. This because you need public works to bury cables, and you also need big boats, etc. Satellites, rockets. You need to melt silicium. Plenty of manufacturing in order for an IT system to exist. Plenty of manufacturing. And the result of all this is that when you look at the energy efficiency of the world economy, here you can see how many constant dollars you get for 1 kilowatt hour of energy, and you see that the beginning of the IT revolution is not really the time where you see the efficiency increasing. Actually, it stopped increasing at the time. It stopped increasing, okay? So the idea that just pouring computers into the economy is going to, by itself, increase the efficiency of the economy is false. It is not the case. And actually today, the global IT system is a global flow enabler. Just imagine that tomorrow morning I suppress the global IT system in the world. I just suppress it. You just cannot manage the plane traffic that you have today without computers. So you save plenty of CO2 from planes. You just cannot manage the flow of car manufacturing today without computers. So I stop manufacturing cars. You just cannot manage the world financial system without computers because basically the world financial system is a world IT system. End of the world financial system, end of banks. End of banks, okay? Etc., etc. So actually, the complexity of the world today cannot be managed only with papers, with paper sheets and pencils. It cannot. And if you cannot sustain the degree of complexity, the economy collapses, and therefore the CO2 emissions decrease. So the idea that the global IT system is an energy saver today and a CO2 emission saver is false. Fake news again. It's the exact opposite. It is a global energy enabler and a global CO2 enabler. Here you have the CO2 emissions in the world. And here you have the beginning of the IT revolution and the renewable boom. And as you can see, it is indeed a boom, but of CO2 emissions. Now for a couple of figures before we leave. This is issued from a report that the SHIFT project, which is an NGO that I founded 7 years ago, has just issued recently on the footprint of the IT system. One main figure, the footprint of the IT system today in the world, that is all the emissions that you have if you sum up manufacturing the equipment, both the network equipment, the servers, and the terminal equipments, and the electricity required to operate the equipment. If you sum up all that, it represents 4% of the world emissions. That is twice the emissions of the world fleet of airplanes or the equivalent of the emissions of the world fleet of trucks, and it's increasing by 10% per year. There is nothing less sustainable than the IT system. Nothing less. Okay? And it won't last because of that reason. It won't last because of that reason. It's even, so what you see here is from the line, the interesting thing is the amount of energy that you use to manufacture a device, and actually we have looked at a number of elements that you use to manufacture a computer. When you look at the normal, I would say, life cycle analysis, you don't get the elements by one. You get the antimony equivalent, which is not very convenient to address issues. What you can see, for example, is that in a laptop you have 170 grams of copper, which is something you recycle when you get rid of the laptop. But you don't recycle indium, you don't recycle gallium, you don't recycle cobalt, you don't recycle palladium because the quantities are too low. What you recycle when you recycle this, in which you have 40 different metals, is gold, copper, and tin, and that's it. The rest you don't. What is even more annoying is that the amount of CO2 that you emit to manufacture a terminal is increasing over time. What you can see here is that for Apple, for example, the embodied carbon has increased from 60 to more than 100 kilograms of CO2 over time, depending on the generation of device that you buy. So a tablet, for example, embodies much more carbon than a small smartphone, which means that regarding IT systems, first conclusion that you can keep in mind from what I'm just saying is that the only way, or the first thing to do, to be more precise, if you want to do something about the emissions, is to keep the hardware for as long as possible and buy it as small as possible. If you don't do this, you're against addressing climate change. It's very simple. It is very simple. Small things, keep them long. This I've already said. And this is a breakdown of the energy consumption of the IT system. You see it's evenly distributed. So a big chunk is manufacturing. Sorry, I can't see it very well. Production of smartphones is there. Production of computers is there. Productions of connected TV, other production. So production is about half. Operating data centers, networks, and terminals is the other half. So it's almost evenly distributed. It doesn't prevent the IT from saying that actually they are going to save the rest of the world. So what I hear everywhere I go is that all this doesn't matter because we are going to make the other end user sectors smart buildings, smart cities, smart whatever you want. And so our own footprint is not an issue because we are going to lower the footprint of everybody else. And again, when you look at the global CO2 emissions in the world, it doesn't work. They increase. So we missed something, obviously. Okay. Last thing, so this is the elements that we use into the IT, or actually, yes, into the IT system. And what you can see is that most of them are not recycled. All those that are in red are recycled for less than 1%, basically because the concentration that you get in the finished product is too low, and you cannot extract, and it's mixed up with plenty of other things, and you just cannot get it back easily. Easily meaning at a reasonable low energy expense. Okay. I'm finished. So in rough figures, we sit on energy that are our mechanical slaves. This energy is not sustainable. Decreasing it voluntarily is triggering a recession. Not decreasing it voluntarily is triggering a recession later on, because it will decrease anyway, but at that time, climate change will be harsher. And in that big picture, the IT system is an enabler of the global problems coming ahead, and not a solution to the global problems coming ahead. Thank you.